Okay. So, hello everybody. Again, we will start today with the next part of our lectures. This will be today about, and probably three more lectures, including today's, or like one more, where we will be talking about dynamic programming. So what is the core idea about dynamic programming? In dynamic programming, like, do you know what induction is, right? I guess you know. So when you want to prove something starting from 1 to you want to prove something, when you go from n to within the step part of the induction proof, you take from n to n plus 1. Or more generally from 1, etc., n to n plus 1. The dynamic programming is the similar idea, is that you can get the value of the problem, the answer to the problem, from getting the answer to the smaller problem. So consider a simple algorithm that calculates Fibonacci numbers. If n equals 0, then return 0. If n equals 1, then return 1. And otherwise, you will return fib of n minus 1 plus fib of n minus 2. So the Fibonacci is pretty simple sequence, so like f sequence equals to fn minus 1 plus fn minus 2. So and our problem here is to calculate their nth Fibonacci number. Can you tell me why this algorithm will be slow? What is the asymptotics of this algorithm?
Maybe because we call two functions in return.
Yeah, that's the right point. So what is the complexity of this algorithm will be? Can you imagine? Okay, so let me...
2n approximately.
Sorry?
2n?
2n? No, unfortunately not. So like how this recursive function works. So we had Fibonacci of n, then it calls Fibonacci of n minus 1, Fibonacci of n minus 2. This one itself calls Fibonacci n minus 2, Fibonacci n minus 3, and this one calls Fibonacci n minus 3, Fibonacci n minus 4, and etc. So like it goes recursively. Each time you kind of divide into two halves. And the problem is that the number of these calls is growing exponentially, as you can see. Here, to be more precise, the number of calls is exactly the Fibonacci number, because we stop only when it becomes small. But you can see that some values you calculate several times. For example, you calculate Fibonacci n minus 2 here, and Fibonacci n minus 2 here, Fibonacci n minus 3 here, and Fibonacci n minus 3 here. So, could you suggest how to improve their algorithm in order to not calculate each of these Fibonacci numbers several times?
hold the value of already calculated function in some variable, then we just call this value from the variable, so we use memory.
Kind of, great. So kind of you create a huge array with Fibonacci numbers there and fill it with -1. And you simply, as Konstantin said, we simply store the value in there. So if f of n not equal to -1, then return fn. Otherwise, return fib n minus 1 plus fib n minus 2. Okay, that's already very good. What is the complexity of such an algorithm? Can you tell me? Depending on n.
All of n?
Yeah, it will be linear because you calculate this thing only once, right? So this is almost as dynamic programming is thing. We store the answers for the smaller ones, and you calculate from it the answer for. Oh, sorry. I forgot to. Fn equals that. I forgot to save. Okay. This thing kind of named like dynamic programming with memoization, so that you have a state. The state in this case is n. And you ask for smaller states. You ask for state n minus 1 and state n minus 2. And if you already asked this state, like here, then you simply return the answer. So it is named dynamic programming with memoization, because you know there are some answers for the state, and if we don't know the answer, then we calculate. Okay, but we can improve a little bit this algorithm in the terms of not complexity but the running time, and how typically their dynamic programming algorithms are calculated. So no, you typically you can use this approach with the recursion, but recursion itself gives some overhead for the computation, so it will kind of be 2 times slower than the following algorithm. We have similarly like this function. So like if we call n, then we simply had to get an answer from n minus 1 to n minus 2. So we can simply go from left to the right and calculating the Fibonacci number that we need. So we say f0 equals 0, f1 equals 1, and then for e into n, we tell fi equals, we know that we calculated all the answer for all the states that are smaller. Then fi is simply fi minus 1 plus fi minus 2. So nothing hard is here. So this thing is named kind of dynamic programming. I don't know why it is called. I would like to name it like typically state programming, but it is as it is. Okay, are there any questions right now?
No, it's clear.
Okay, great. Yeah, I hope that it's clear, because it's kind of like we start from the very beginnings, and like we will go like there is nothing hard will be today, I think. Okay, now consider the next problem. So you have a row of cells from 1 to n, and you have a grasshopper here. I'm not very good at drawing, but like, let it be something like that. Like we have a grasshopper, and during one turn, grasshopper can jump on one cell or on 2 cells. And the question is, how many ways the grasshopper can jump, in how many different ways the grasshopper can jump from 1 to n? So you again want to kind of shrink the problem to their smaller ones. You want to calculate the result for their cell n, and for that you can use the results for smaller ones. So can you tell me, probably?
So in cell n-1, there's only one option for grasshopper, is jump to cell n, and in cell n-2, there's 2 ways. One is jump to n, and the other is jump to n-1 and then jump to n.
Yeah, but we want to calculate answer of n to, like, how we can jump to their nth cell, from which, like, as Konstantin said, we can jump from n-2 and -1, right?
Yeah.
Yeah. And what are the jumps here? From n-2, we can jump on height, on their length 2. Because why I'm considering only this condition? Because if you jump on 1, you already calculated it in n-1 answer.
Yeah.
Okay, so then we can jump from n-1. So the total number of different ways to get to the nth cell is simply answer for n, which is equal answer -1 plus answer n-2. So, and you can see it is simply their Fibonacci numbers as we had previously. Like exactly the same. So you can go from left to right and calculate this as necessary. Suppose now that we have a turbo grasshopper, that it can jump up to k cells. So like this is k plus 1. So it can jump on 1, on 2, and on, like, on everything else in between until k. So how will their algorithm change? What will be their, how to calculate their answer for their nth cell?
So it will be k terms in this situation. From n-1, n-2 to n-k.
Yeah, exactly. But how will it look in the algorithm? So we know that answer for 1, how many different ways we can jump from 1 to 1. Like I'm trying to write a code right now. So so we should like, there are two things. So it's kind of in the induction thing. You go from the smallest to the next one. And from the other hand, you need to know the base. So when you prove something by induction, you have to prove the base first. So what is the base here?
Answer for 2 plus 1.
So answer for 1. What is answer for 1? It is simple. How many ways we can jump from 1 to 1?
I don't understand why we need to jump from 1 to 1.
Okay, you want to have base from 2, right?
Yeah.
Okay, let's think that it's 2. So what is here? What is answer for 2? Okay, I will open you the mystery. So the number of ways that you jump from 1 to 1 is 1, because you cannot jump there any other ways. So you just have only one way to get to their to their position 1. And for 2, how many it will be?
There is also 1.
Yeah, there is also 1. Yeah. So you have only one jump, like to the second, you have only one jump there. So, and then we calculate for all others, for e equals 3 to n, for j equals to maximum of 1 and j minus k, to, oh, sorry, to I, of course, I minus k, and to I minus 1 ons of I plus equal to ons of j. Okay, so we simply go from there. So for example, for 3, there will be 2 ways, one from 1 and one from the second position. That is why you place maximum here, because they're like you can jump only starting from the first cell, and sometimes this value will be negative or 0. So we cannot jump from this place because we don't know the answer. Okay, so this is their algorithm for our problem. And I will give you like something to think about for 2 minutes, or probably less, if you come up with this. What is the complexity of this algorithm? Before we come to the question, what is the complexity of this algorithm depending on n and k? So we have 2 variables, we have n and k, and what is their complexity of this?
Probably n multiplied by n minus k.
Why n minus k? So how many iterations does this loop has?
N iteration.
Okay, how many iterations does this loop has?
From 1 to I minus 1, and I is...
No, we have here maximum from 1 and I minus k.
Yeah, but in worst scenario, we have from 1 to I minus 1. Yeah?
Yes, that's true. But how many in their not worst cases you think of? How many, if this maximum is always I minus k, how many iterations does this loop?
K minus 1?
Yeah, to be more precise, k, but like, doesn't matter. Okay, and when the worst case, you can see that the number of iterations that does this loop is less than k. It is always less than or equal to k. Because if this is negative, then I is less than k. Then from 1 to I, it is also less than k. And what is the complexity then?
N k?
Yeah, it's simply n times k. So the question is how to get from n times k to O of n, simply O of n. Can you come up with their algorithm that do this?
I don't know exactly how we should like, but there is the same idea as for Fibonacci number. We calculate things several times, and we just need to store this information and not to calculate it again. And this will reduce the complexity of algorithm.
No, you will still have this inner cycle, in the inner loop that turns k times. Like even then, you even here you already calculated the previous ones, and it still works in O of n times k. Okay. So let me explain the approach that typically done in this case. Let us calculate together with transfer the prefix sum. So sum I equals to sum I minus 1 plus answer of I. And then this part of the algorithm will be like ans I equals to sum to I minus 1 plus, minus sum of max 1 I minus k plus 1 or minus 1. So you just calculate the prefix sums here. So you're going from left to right, and you know, for example, for ith position, for j position, that what is the sum of all their elements in the front? And then you simply like tell that sum I minus 1, this is their prefix sum form. So like, if you imagine on the line, so you have here for I minus 1, blah, 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 I minus k. So you have to take the sum of everybody here, minus sum to here. And then you will get exactly the sum of all the elements in between. That's it. Nothing very complicated. Okay. Now consider that some of the cells are forbidden. So you have an additional array forbidden that will tell for the cell whether it is forbidden or not. How to update this algorithm so it will work with forbidden cells? So let's probably do something here. I will try to explain you. So you know that you calculate their last jump for the previous cells. So how many ways to jump from 1 to n and pass this forbidden cell? How many ways there are? Since you cannot jump on the forbidden cell. Okay, so you simply can do here if not forbidden, j. So if j is not forbidden, then we can jump from it. Otherwise, this answer will be 0. From this, like the number of ways that to pass through the forbidden cell is 0, because you cannot stand in a forbidden cell. Thus, you either do this, or, which I think simpler, so you don't have to change here anything, you just tell here, if forbidden of I, then you know that the answer to pass through it is 0, and continue. So you just check whether right now the cell is forbidden. If it is forbidden, then we say 0 to the answer and continue. Why it is the same as previously? So when you check here the forbidden, if it was a forbidden, we increment it by 0. So this is exactly what we did here. So we set it to 0, so when you add everything up, you will get that this place 0. Okay. Questions right now? If you don't have questions, then we move to the next problem.
Can we calculate this number using the total number of forbidden cells, or it's impossible?
I think it's impossible because the cells itself are irregular, so they don't have any structure. So you have like additional array forbidden. It has some structure, unfortunately. If there were no forbidden cells, then we can apply some other algorithm, like to calculate it, and it will work faster. So, suppose right now that each cell is either forbidden or has some amount of money. So, if the grasshopper jumps to the cell, then it gets C of I. If he gets to the cell I, then he receives Ci number of coins. If Ci is bigger than 0, bigger than equal than 0, can you tell me how to get the most number of coins that you pass from 1 to n? Under a condition that all coins are bigger than 0.
So we need to jump at every cell which is not forbidden, and for this purpose we need to use the minimal not forbidden action.
Yeah, so that's exactly true. If all Ci's are greater than 0, then we can greedily take each coin from everywhere. Okay, but our life is not very easy, and sometimes a grasshopper has to pay some number of money. So if Ci is less than 0, then he will pay some amount of money. So, again, how to calculate the dynamic programming. So you want to know the answer for n, and you want to know what is the maximum amount of money we could get if we jump from n minus 1, n minus 2, n minus 3, and etc. n minus k. So it is exactly the same, but right now we should calculate the maximum instead of sum. So if the element is forbidden, then we set it to minus infinity. And then simply ans I, and also, so yeah, we also have to change the base, but like, let's first, so we tell that answer for I is minus infinity, and then you will check just max of ans I and ans j plus ci. So we try to jump from all the positions that are by k to the left, and we add the number of coins that we get from their position n. Can you tell me what is the base? What the base is? So we want to know the answer for 1. How many coins do we get if we jump from position 1 to the position 1?
0.
Almost, yeah. It's kind of 0 or C1. This depends on how we state the problem. If they're not, like, their first cell has some number of coins also in their definition, then we should add this number of coins to the answer. Okay, and then we just go from 2 to n. And calculate everything. So, is there any questions right now? So, again, the complexity of this algorithm is O of n times k, which can be reduced to O of n, because you can see that this maximum is simply, so if you calculate this more properly, so it is answer for I is equal to Ci plus maximum of ans I minus k ans I minus 1. And you can see that at each step it is almost as calculating maximum from their Q. So for their answer I plus 1, it will be Ci plus 1 plus maximum. You don't have I minus k, but you have right now ans I minus k plus 1. Then you have ans I minus 1, and finally ans I. So you just simply, you kind of, for the next position, you just take their first value that you take maximum from, you take from this one, and you add a new one to that. So this can, like, as far as you remember, we did the maximum on the Q, we did minimum on the Q, but you can simply calculate the maximum on the Q using the same algorithm. Okay. The question. Suppose, like, these problems are very good, like to find their minimum or maximum something. But what is, for example, if we are asked to please tell me all the cells that you visited in the best way, on the best path. So what should I do to restore the best path? Okay, probably it will be not so easy, so I will explain it. So you just create a new array from and you just, for each cell, you will remember the previous cell from which you jump onto us. So if ans of I is less than ans of j plus ci, then we tell ans I equals to ans j plus ci, and we say that we jumped to I from the position j. So, and to restore, then you just x equals to from of n, and then you do while x is not equal to -1, you continue answer dot push front x, and you tell x from x. No, like that would be not answer, but that would be path. So you just go, really even like that. So it's not from n, like x equals 10. So you jump by the from links. So you go from, and like add to the DAC or like Q as you wish by adding all the elements that we visited on the path back. So that's how you restore the path. So typically in dynamic programming, it is sometimes asked to please restore me the answer. And the simplest way is to maintain from which state did we go there. So here we mark that to the state I, we get from the state j, and then we know already how we got from the state j, then we should take like the from of j and etc. And that's how you restore the path. Questions? So on the simple problem, we understood how to do a dynamic programming in this simple way and how to restore the path. Okay, let me make the problem even harder. And you know that grasshopper jumps. So if the last jump of the grasshopper was j, then the next jump can be either j minus 1 or j plus 1. So this means that if the jump of the grasshopper was of length j, then it cannot get very fast, but it cannot get very slow. So it just simply the next length of the jump will be either a g minus 1 or a g plus 1. So can you tell me what will be the state right now? So as usual, this state should consider like the elements on which the algorithm depends on. Obviously, you should know their cell. So the cell itself is a state. What also is but like it's not enough because there is somewhat last jump that should be maintained. So what will be the state then?
It should be j minus 1 at least.
To be more precise, why do you need j minus 1? You need only j. So the state will be the cell and the last jump. So we maintain the cell and how high the last jump was. So you simply, and you want to calculate, so there are two ways on how to update this thing. But like if you want to calculate the answer for ij, from which states we can get into it. So like what are their steps? From which states we can go to ij, where your new cell is I and your last jump was j. From which states we could get to ij. Okay, let's start from this.
Minus 2j.
I minus 2j?
Yeah.
Why 2j?
Because the previous state was I minus j.
Okay, so the previous state is I minus j. Okay, good. That I understand.
And the previous of the previous is I minus j.
Okay, no, that's you're trying to overcomplicate a little bit. So since the last jump is j, then the previous state was I minus j. Okay?
Yeah.
What can be the jumps that can be at that I minus j? Which different values? Okay, let's start from the simple. How many states you get from to ij? How many states? Since you know that the jumps are j minus 1, j, and j plus 1.
So there are 3 states?
Yeah, there are 3 states. So, what are the states? So we know that we have 3 states and we know that the cell from which we jump is I minus j. What can be the jumps that we can get to I minus j? What is their second parameter?
Intermediate state?
What, sorry?
Intermediate state.
Why intermediate?
The second parameter is j minus 1, j plus
Yeah, so this is j minus 1, j, and j plus 1. Yeah, that's simple. Why so? Because when your jump is j plus 1, you can, like from this state, you can jump with j, j plus 1, and j plus 2. So exactly you can jump on j. Here you can jump from j minus 1 to j plus 1, and here we can jump by j minus 2, j minus 1, and j. So like only in these three cases you can jump on j. So and then you simply calculate. You just have for I from 2 to n, do for jump from 1 to I, and you just say answer for ij equals to maximum for ans I minus j. Oh, sorry, my bad. For last j equals to j minus 1, j plus 1. Then you just tell ans ij equals to maximum of ans I minus j last j and plus ci. So you iterate through all the cells, you iterate over the last jump, how long is the last jump, and then you calculate what was the jump on the previous step. On the previous step, this jump can be only j minus 1, j and j plus 1, and you take the maximum out of them. So, of course, you can do this a little bit vice versa. So you know that from answer ij, you can jump in 3 states only also. You can jump to I plus j minus 1, j minus 1, I plus j, j, and I plus j plus 1 with the last jump of j plus 1. So, and we simply can do maximum knot out of I plus j, but we will do the dynamic programming forward either. So this is what's kind of calculate backwards, and right now we're calculating forward that. So instead of last jump, now we will have next jump, and we will say ans of I plus next jump equals to maximum of ans I plus next jump, and answer of ij plus c I plus next. So in this algorithm, we are doing this forward. So instead of getting their answer from the previous ones, we're doing forward, so we relax this answer that we already know to the next ones. Okay, so that's it for Grasshopper. Do you have any questions? Okay, if you don't have any questions, like let's move to a little bit harder, like not really harder, but a little bit different. And of course, you can do this recursively. You just like call their get me answer of ij, and like you ask for the answers for these guys, and if the array state for this state is not -1, then you know the answer for that, and you just can compute. You can just simply return that you already calculated this. Okay, so the next question is the following. So you have a rectangle, and in each rectangle, again, there is written like the number of how many coins we should pay or either be paid if we step on this sum. And we will have a turtle there. The turtle can only go to the right, one step to the right, or one step down. That's all the turtle can. So, and we want to calculate the maximum amount of coins that we can get if we go from the topmost left to the rightmost here, rightmost bottom. Again, suppose we are right now at position ij. From where we can get to ij. Like Like let's start a little bit from the base. So the base will be these cells, and these cells. This will be the base, where at least one coordinate is 0. So you can simply calculate the maximum number of that we can get is simply the sum on this prefix. And here is the same. Because there is only one way to get to each cell. To this cell only from the left, and for this cell only from the top. So again, the logical thing says us that the state is the cell at which we are right now locating. Can you tell me the step for this induction? From which states we can get to ij?
So there's two options from I-1j or from I j minus 1.
Yeah, exactly. You can go from here or from here. So the algorithm becomes very simple for I. Okay, let me just do the base case ans of I. So ans 0, 0 is C00. Then for 1 here, it is answer like that is ans I minus 1, 0 plus Ci 0. Then the next case, but with like the row, the column, like 0i equals to ans 0i minus 1 plus C 0i minus 1. And then finally, we calculate the whole rest thing, so like from 1 to n, do for g to n, and we want to calculate answer for ij, and we know that we can go there only from 2 other states, and we just simply say maximum of ans ij minus 1, ans I minus 1j, plus C of ij. Okay, good. Now suppose that we want to restore the path. What should we do?
We should backtrack.
Yeah, we should backtrack, but to backtrack we need to.
By state, previous state.
Yeah, but you have to write backtrack somewhere, right? No, that's a good point. So we need from, which tells us from ij, from each cell we come. Yeah, that's good. So how this code will be changed?
I'm not sure. We should somewhere remember the previous state or action.
Yeah, exactly. You should store. So, okay.
Well, store anything.
Sorry?
I'm not sure. What are we storing at the answer array?
Answer array calculates how the biggest amount of coins that we can get for the path from here to ij. So this is ans ij.
Okay. So we need an argmax then. We need argmax, and we need the I will hold it an array with path state. So we need just in the sum. We need to store okay. Special rule, because it will be just not calculate the sum. If we will not rewrite the sums into the array, we just need to store the previous state, and then you can backtrack and also calculate the sum.
Yeah. So approximately like that, but okay. So let me write it. So simply it will be like that. So we check two states if ans of ij is less than ans of I minus 1j plus Cij, then ans ij equals to ans I minus 1j plus Cij, and as you said, you store there from ij equals to I minus 1j. And the same goes for the second case. If ans ij less than ans ij minus 1 plus Cij, then you are doing the similar thing. So like you update the answer. Like this is how you do kind of arg maximum, as Elizaveta said, but like it is more explicit because you don't have the function arg maximum, unfortunately. Okay, that's okay. Yeah, and if, for example, we have forbidden cells, what should we do? For example, some of the cells are forbidden.
Just check what we do.
Yeah, we just check. Yeah, that's true. So we just check whether the cell is, whether we can go over the cell and this thing. Okay, so we have a little bit more time. Okay, it seems like you are starting to warming up. So like 1 a.m. is too early for you. So you're kind of warming up later. And we had a good time at 5 p.m. So like typically have 5 p.m. So like you're already in the good shape. Okay. Now we want to solve the following problem. You're given an array of integers, like 1, 3, 5, 2, 3, 4. And you want to calculate the longest increasing subsequence. So for example, here the longest increasing subsequence will be 1, 2, 3, 4. And we can put somewhere here 1, for example, and it still will be 1, 2, 3, 4. Again, the first thing that comes to mind is that the state of the algorithm will be the self. So, in other words, ans I is the longest increasing subsequence that ends in I. So we want to calculate this. So like our ends at I. And you know the answers for the prefix. Can you please tell me how we will perform step? Sorry, I don't hear pretty well.
So sorry, I can just.
No, I'm just increasing their level of their like speakers. Can you tell again? What is your question?
Because we just start from the left to the right, and we just avoid doing the same job that's already pre-calculated. So, what do you mean by step?
Okay, yeah. So suppose we are right now staying at the position I. From which states we can get to the, like, we want ans I to be the longest increasing subsequence. And you know that their element at position I is Si. from which states we can get to the state I.
So we can get to I if this element is less.
Yeah, exactly. Yeah. So
and it's better to find a minimum element before I to start from this.
Why minimum? Okay. In this sense, minimum. Okay. So yeah, you just to the position to the state I. You could jump everywhere where Sj is less than Si. That's what Konstantin said. And since we are trying to find the longest increasing subsequence, we should go over all elements on the left, and if Sj less than Si, we should try to tell the ans I equals to ans j plus 1. So we add one more element there. So we take what was to the place j, and then we plus 1 plus our element itself. So the algorithm becomes very simple. So for I from 2 to n, do for g from 1 to I minus 1, do if Sj less than Si, then ans, we are doing exactly like that, ans equals max of ans I and ans j plus 1. Okay. Again, now we want to restore the longest increasing subsequence. What should we do? Again, our typical algorithm for the restoration is that we maintain the array from. So from each cell, you know from which cell you get there. So what should we do here?
But that's not for array, just for the is element calculated the max. No?
Yeah. So it is exactly the time where we calculate the maximum. So it's, sorry. Okay, I don't know why, but your connection is not very good, or probably my connection is not very good. I'm hearing you like kind of no worries, but like it's internet connection. But I think you already got it. So like if Sj minus 1 and if ans of I less than ans j plus 1, then you tell ans I equals ans j plus 1, and you set from I equals j. Simply like that. Okay, the only question which is left. So we calculate for each I the longest increasing subsequence that ends at I. But our original problem were to calculate the longest increasing subsequence in the array. So where we should find the answer? How we should find the answer, to be more precise.
So we need to change I to maximum of this array And we will find, no.
No, you're almost right. You're almost right. We know that ans I is the longest increasing subsequence that ends at I. So to get their answer for the whole problem, we just simply need to traverse through all the elements and get the maximum answer that we have there. So we just iterate over all ending positions of their increasing sequence. Okay, do we have a little bit time? Yeah, I think we have a little bit time. So what is the complexity of this algorithm? It seems I'm doing my job not very good. Because you should be able to calculate the complexity of such algorithms in no time, like on reflexes. So what is the complexity though? Any ideas?
So we have two cycles for one is from 2 to n, and second is from 1 to I-1. So it's approximately n squared.
Yeah, exactly. It's all of n squared. Okay, so let's breathe out a little bit. So like that's kind of the necessary part that we done for today is almost finished. So like right now I will explain you, I will try to give you an intuition how to do in n logarithm n time. You can see that here you ask for the elements in the prefix that are smaller, right? So you ask for the smaller and you kind of relax their answer over them. To which data structure is it similar? That we already passed.
Can you please repeat?
Okay, so we in their algorithm we want to take all their answers that correspond to the elements that are less than ours. That's currently ours. So which data structure supports operations on their smaller elements?
That preserves the minimum elements in the root. I just don't.
Why the minimum element in the root?
Because you're asking this question.
No, I'm asking the question. So, like, let's consider how you update this algorithm, like how you update the dynamic programming. You go over the prefix, and you look only on their elements that are less than Si. So, which data structure helps us to get all their elements that are less than fixed one?
Trees.
Yeah, trees. Okay, great. So, let us store in our tree, at each node, we will store the last element and the answer for this element. Then, at like your whole tree, like as you remember, with the trips, we could maintain the sum in all the subtree. Here, instead of sum, we maintain minimum. It can be recalculated in a similar manner. So, to get their answer for I position, you just simply cut the tree by Si into two trees, like tree like that and tree like that, and you simply take their sorry, not minimum. We want to maintain maximum, and you simply take the element that is on that is maintained in the maximum. So there is some other element Sx ans x, and also we maintain the maximum in the subtree. So if we maintain the maximum in the subtree, then simply when we split, in the root we will have the maximum for the subtree, which is the whole tree, and this exactly corresponds to all their elements that are less than Si. And we can get the answer from that. So just take this maximum and plus 1 it. So now we have the outer loop, and then we do not have inner loop. We just split their tree into parts, which are, as we discussed, is logarithm n. So in total, you will have of n logarithm n complexity for the algorithm. Okay?
I understand why we use the trips, but not understand why there is a maximum in the root.
Yeah, you should maintain, like in the tree, as you remember, right? For example, we maintain the number of elements in the subtree, like in the trips part. Do you remember that?
Yeah.
Okay, so instead of maintaining the number of elements, we will maintain the maximum value in the subtree.
Okay.
Okay, so the maximum value over ans j1s. So you take maximum value. And then when you split, you will have here all the j's for which sj less than si. So in this tree, our maximum in the subtree will be exactly the answer for the problem.
I understand.
Okay, and then of course at the end you should insert si and answer I to the tree. That's it. Any questions? Any more questions? I would be happy to answer. Is there any? Okay, that's it then. See you next week then at Tuesday again. We will continue with dynamic programming there.
Okay, thank you.
Okay.
Bye.